Okay, the last test for the series is the root test. So this is almost similar to the ratio test, but then this one consider the root. Okay, the root and the absolute lah. Okay, so in the cases where it is difficult or inconvenient to find the limit required for the ratio test, so the root test is sometimes useful. So we have three conditions here. Actually, the condition is almost the same to the ratio test. Okay, so for the first one, it says that if the limit for the root of n, absolute en, equals to certain value of L, that is, this L is lesser than 1, then the series en is absolutely convergent and therefore convergent. So the same as the ratio test. Okay, and if the limit of the root of n, absolute en, is L greater than 1, or you get infinity, then the series is divergent. But then if you get the limit is equals to 1, then the root test is inconclusive. You cannot make any deductions or conclusion. Okay, this is the root test. We have the condition. So now we try to do the example. Okay, example 27. So let us try example 27. Okay, example 27, the given series is okay, n equals to 2 to infinity. 4n minus 5 to n plus 1 to the power of n. Okay, so just for a tips, usually the type of series that having like a power of n like this, it is suitable for the root test. Okay, because this n would somehow be cancelled out later. So when you see something, the series something like to the power of n like this, it is you can try to use the root test. Okay, okay, so by using the root test, okay, limit n goes to infinity. So we have root n absolute for n minus 5 divided by 2n plus 1 to the power of n, and then we close the absolute. Okay, so now we have this form. So what we can do, we can simplify it first. So since we have the root of n and we have the power of n right here, so this can be actually cancelled out. So what's left is I still put the modulus or the absolute. So I have 4n minus 5 divided by 2n plus 1. Okay, now you have this form. So do not remove the modulus set because there is a minus something here. So somehow this one cannot be a positive number. So we stick with the modulus first. But we can simplify to solve the limit. So I factor out the n. So n4 minus 5 over n. Then n 2 plus 1 over n. Okay, close. Okay, so we can cancel out this n. And what's left is okay, 5 over n. This one limit as n goes to infinity, this one becomes 0. This is also 0. So what's left is 4 over 2. Okay, absolute of 4 over 2 is absolute 2, which is just 2 lah. Okay, so we get the L, the limit is 2. So 2 is greater than 1. So based on the condition, we can conclude that the series is divergent. Okay, because this is the reason. Okay, next example, example 28. Okay, given the series is, if you look at this is actually the alternating series. we have ln n plus 1 to the power of n. Okay, so we apply the root test. So we have root of n, and then we have absolute, so negative 1 to the power of n over ln n plus 1 to the power of n, and we close the absolute. Okay, so now since this negative 1 to the power of n is inside the absolute, we know that it will become 1. Okay, I change the color. This one would become 1. And we can actually, okay, this one become 1, then we can remove it lah. So this one become, is simplified into sedan, okay, 1 over ln n plus 1 and then to the power of n. Okay, so I remove the absolute because I know it will always be positive. Okay, so okay, this one can be rewritten back so that you can see how can we cancel out the root n. So we have root n, so 1 over ln n plus 1. Okay, close. This is actually the same as to the power of n kat situ. Okay, because 1 to the power of n is just 1, so we can write it that way. So we have root n and to the power of n, so it automatically cancel out. So what's left is just 1 over ln n plus 1. Okay, so this one you cannot adjust. So we try to plug in n as infinity inside. So what we have is, so ln n, you substitute with infinity, so you get ln infinity. So this somehow the denominator would become infinity. So 1 divided by a very big number, the limit would be 0. Okay, so 0 is lesser than 1. Okay, so based on the condition from the root test, therefore the series is convergent. Okay, or you can say that the series is absolutely convergent, then it is also converge. Okay, convergent. Okay, next example. Example 29. Okay, betul tak example 29? 27, 28, okay, 29. I think this is the last example for the root test. So we have given the series is 5n minus 3n to the power of 3 divided by 7n cubed plus 2 to the power of n. So when you look at the series that is something like having a to the power of n, we can use the root test. Okay, let us find the limit. So we have root n, and then we have the absolute 5n minus 3n cubed over 7n cubed plus 2 to the power of n, and then we close the absolute. Okay, this one can be simplified. So we have to the power of n and also the root of n, then we can cancel out. What's left is just 5n minus 3n cubed over 7n cubed plus 2. Okay, this one. So I do not remove the absolute because there is something minus kat sini. So somehow maybe it still needs the modulus. Okay, so this one we can simplify to find the limit. So I factorize the biggest n that having the I try to factor out the n with the highest order. Okay, so n cubed. So this one become f over n square minus 3 over n cubed 7 plus 2 over n cubed. Okay, so now if we, okay, this one can be cancelled out. Okay, now if you plug in n goes to infinity, then you know this part would be 0 and this also would be 0. Okay, so what's left is just okay, absolute. Okay, this one still has absolute, do not remove yet. So you have absolute -3/7. Okay, so absolute of -3/7, this one become just 3/7. So 3/7 is less than 1. So by the condition of the root test, therefore the series is convergent or converge, or you can say that the series is absolutely convergent and therefore it is also convergent. The series is, betul tak, we look at the condition back. Okay, the series is absolutely convergent and therefore it is converge. The series is okay. So this conclusion is important, so make sure you have the conclusion whenever you solve or you try to find the limit or the convergence of the series. Okay, so this is for the root test, the last test.